then changing the process. All of that you have to know. Then we started the, remember when we started to talk about digital, we talked about the control as on-off, control to mode control. And when we started to talk about that, we started to talk about hysteresis. What does it mean? That we never send output to the final control element on, off. We work with pressure. It's called in the digital Schmidt pressure. Below certain level, it's off. Above certain level, it's on. And in between, it's latching from where you came from. So if the error is less than 0, you turn off. If the error is greater than 0, you turn off. And we call it on-off control versus continuous control of the LTO. We started to talk about some Boolean equation, but we didn't do much. You are very good about that. You have no problem, right? You are okay. So what's the output here?
What's the output?
What is the output here?
D.
What is D?
D is, let's see.
No way. What is D?
D is
The output. Is that or that? Right?
Yeah, either or.
Right. So D is equal to this expression plus this expression, and then you can work with minimization and you can do all of that. You took some problem. We didn't talk about the, I saw it in your book. The processor has 3 lines: the data lines, the address lines, and the control lines. Is data line bidirectional or unidirectional?
Is what?
Is it bidirectional or unidirectional? The data bus?
No, it's bio.
By.
Oh, of course.
It's going back and forth.
Why it's bidirectional?
I don't know. Some people just want to be.
No,
Oh.
because you can read or write from memory, right? If it's read-write memory. So the data bus going from the processor to a memory, for example, RAM, right? You can read-write from it. So it's bidirectional. Can go this way or that way. But how about the address bus? Unidirection, because it locates one location in the memory and then the control lines and all of that. That was in your book. Did we talk about tri-state buffer? What is tri-state buffer? Why it's called the tri-state buffer?
I want to say it's a 3-step buffer.
Three states. What is, give me one state?
Positive.
0. The other 1, because the input here could be 0, 1. Okay, the output doesn't take the state of the input unless you enable the buffer. So that's 2 states. If you disable the buffer, there's complete isolation. That's how many signal can share the same line. When you start to talk about the data bus state of them from several IOs sharing a signal. So tri-state buffer is 3-state buffer. 1, 0, or complete isolation. So if you enable that, if it's active high and I put high signal, have 0, I have 0. 1, 1. That's 2 states. If it's disabled, I put 0 here, total isolation. That has nothing to do with it. And this can go to the line. Right? Okay. That's the basic comparator. Compares voltage and produces a digital output. We used that also in one of the lab when we compared the signal and we started alarm, if you remember. So in PLC, that's the instruction. Greater than or less than. You can do exactly the same thing in PLC. That's, what do we have here?
Here.
Temperature voltage, right? Okay. And if the temperature is greater than this, the output is true, right? And here we have the pressure. If it's greater than 2 as a voltage signal, that will be true. So the alarm should show what?
When both of them are bad.
Both of them are above the limit. So it's the temperature above the limit, and if I put or, either one will get me to trigger the alarm. We had some of that. Now, we talked about a digital to analog converter. Some of you tried to put it, remember? Digital to analog converter. And then, when we weren't very succeed, we did the summing amplifier to do exactly the same thing. So, if I have V reference 10 volt and I have 8 lines, what's my resolution? If I have V reference as 8 volts and I have 8 lines, what's my resolution? 10 over what?
256.
Very good. Okay. And the maximum voltage is one step below the resolution. And we worked with it and we did our own. Then this is exactly the same circuit we used in digital to analog converter in our way. And then we started to talk about analog to digital converter. You remember when we talked about the ramp up and all of that, and we did our own? Okay. Now, this is very important. Read this statement. What do we have here? We have the analog input signal, and we need to take the analog input signal to A to G converter, right? Analog to digital converter to represent it in the computer, so we can do the control and then go from D to A to send the signal to the final control A. What do I have here is sample and hold modulo. The sample and hold modulo, when it closes, you have the signal in and it charges the capacitors. So when it's open, it holds the signal here till the A to G converted the signal. There's conversion time. So all what I care about, the sample and hold circuit function is to hold the analog input signal constant till the analog to digital conversion process is complete and it is connected to the analog to G.
C is the buffer, is it?
What is it?
C is the buffer.
What's C?
The capacitor.
No, the capacitor, see, when you, the computer sampled the signal all the time and they switch to the other one.
Sorry.
When you go to the analog input module, it sampled that and then it switched to the second switch and the circuit complete. As it sampled this one, the switch is closed, the sample and hold. That's charged. So when it opens, it's holding the signal. And it's not going to discharge because that's isolation, very high input impedance. It's not going to discharge through that. No, it's holding the signal till the A to G converter take the analog signal and switch it to the digital count based on the resolution. So you have to understand why we have it, and then it's connected to what? A to G, analog to digital converter, or of course analog to digital. Review that, okay? You understand what I'm saying about the processor? Sample one by one, so when it sampled this and switched to the other, the circuit is open, holding the voltage, so that there is conversion time that takes till the digital count. What else here? That's the process control using, and then we started to look at A to G, G to A. Here is the temperature, and we have the signal going to A, that's the V reference. So based on that's going to be 2 divided by 256. That's the resolution. And the maximum voltage, this going to be is the signal, the maximum minus the resolution. You remember we did all of that? And then the computer will manipulate that by PID loop and everything. And then we're going to go to digital to analog converter to send the signal to the image. That's all what we did. We came from sensor, take the temperature, convert it to an analog signal, either voltage or current, and then we used A to G to convert it to digital count. We started by the computer to manipulate the signal to send the final control element. So we came from digital to analog by the opposite. A to G to the computer, G to A to the final control. Is everyone okay with that now? Okay. So, chapter 4, we started the thermal sensors. We talked about you remember we talked about RTG, resistor temperature detector. We talked about thermocouple, and we talked about thermistor. And we used the back of the book to learn how to read. But in the final, really, you're not going to have book, they will give you the value. That's similar to the test 1 and I believe test 2, that time. Okay, and we started to talk about the metal resistance increases almost linearly. And if you look at that, platinum is much more expensive than the nickel. Why? Because it has more linear, right? And you know, so it's better. And it gives you wider range than that, see, for the same temperature. We started to talk about that. And then if you see, you remember, we did linear approximation and it was quadratic approximation, we skipped it. So that's all what you're gonna see in your final test. And you had between two temperature at T0, and you remember we did the slope and we learned how to get this formula. That's definitely, that's very important. You have to understand that thermistor resistance versus temperature is highly nonlinear and has a negative slope, because you did not, some of you did not do that right, and you're going to see exactly the same thing repeated. So remember that thermistor here is nonlinear, and if you look at the slope, it's negative. This time I wish everyone get 100% in the final test. Then the thermocouple, all what they care about, the Mr. Seebeck, the one who invented that. When he put two, Seebeck, what's his name, Seebeck? Yeah, he's the one who invented that. He discovered that by putting two dissimilar material, the voltage is generated. So you have to remember his name. The Seebeck effect refers to the relation between EMF and temperature in two wire systems. And we used it for measurement. Then we started to look at what type of thermocouple. We worked with three. It's more than that. J, K, and S. And T here is your T measurement, and V is your V measurement. So if they give you the formula in the final test, remember that's your T measurement, that's your V measurement, and that's the two value high and low, high and low. So if they give you this and they want that or this and that, you know how to do it. Signal conditioning for the vapor temperature control. That's the one I said we used the comparator in the lab, remember? When the signal was above the whatever we put here, the alarm was on. When it was below, and we learned how to go from RTD, and we calibrated the minimum, right? We calibrated the minimum, and then we simulated the maximum, and then we were able to use the instrumentation amplifier. And we drove all of that, if you remember. And then we used the non-inverting amplifier also for different gain, and that was the signal, and that was so Wheatstone bridge was used for temperature detector, but we didn't have temperature. You know, if you have real heating element or something like that, we could use it to do that. Sensor, and we calibrate the minimum, and then we put it in the temperature and we measure. But we have to do everything by simulation. So that's also important. And then chapter 9, I think we're done here. Let's talk about that. Process load is the set of all parameters excluding the control variable. We talked about multi-variable control. We said we have crackers coming, right? And we need to control the color of the crackers, if you remember. And we said it's multi-variable. We could control the temperature inside the oven, temperature outside the oven. We can control the temperature speed. We can control the extruder feed rate, right? So you could use multi-variable parameters, or you can choose one parameter. You say, okay, I'm going to control just the heat inside, or I'm going to control the motor speed. Then the rest became what? The process load. So if I say oven temperature, I'm going to control it, then my load parameters include everything except that. Except this. Because that's the one I manipulate, and that's the one I want to control. So we started to talk